Hello and welcome to lecture 29 for the course on aerodynamic design of axial flow compressors and fans. In last lecture we were started discussing about selection of various parameters. Now here if you look at, this is what is representing the global trend for the development of aero engines. So if you look at the major concern by aero industries these days, that's what is mainly focusing on reduction of thrust specific fuel consumption. Parallelly, we are also focusing on various environmental aspects. We are also looking for some special kind of engines which will be addressing the issues related to drag, which we can say we are looking for compact engines, we are looking for lightweight engines. So this is what is representing how my global trend, that's what is going on in sense of expected pressure rise from the engines. And we have discussed, say as on today with the upcoming engines, the maximum pressure ratio, that's what has reached to above 60. So this is what is representing how our global trend, that's what is going on in sense of rise of pressure ratio. Here I am talking about the overall pressure ratio. Now in order to meet the special requirements in sense of say expected thrust specific fuel consumption, we are looking for per stage pressure rise to be higher. So here if you look at this trend, that's what is getting towards say higher on the numbers. What it means, we are expecting per stage pressure rise to be very high, and that's what will lead to reduce the number of stages. Now in order to meet this requirement, one of the parameter what we have discussed earlier, that's what is called diffusion factor, and that's what is representing my aerodynamic capacity of the diffusion. Okay, so it says if you are looking for the improvement of our diffusion factor, the parameter called solidity, that's what will be coming into the picture. So this is what is representing the improvement in sense of selection of the solidity. This solidity we are representing as a chord to pitch ratio. It means we are looking for say higher solidity. This is what is the indication that it say we need to increase our chord, or we need to increase our number of blades, or we need to go with the combination of both of them. Parallelly, there is an expectation in sense of height of the blade. So this is what is representing the global trend for selection of aspect ratio. We have introduced the aspect ratio as height of the blade to the chord of the blade, and we can say we are moving more towards the aspect ratio in the range of 0.8 to 1, and this is what is still it is getting converging. So this is what all is giving us idea how the global trend is moving towards the development of gas turbine engines, special application to aero engines. Now let's move with the next step. So here this is what is representing my compressor cascade. What we have realized, we have different parameters, that's what is coming into the picture. When I say aerofoil, what we are using for our compressor blade, that's what is comprising of number of parameters. Some of them we have discussed as air angle, say my flow angle, incidence angle, deviation angle, camber angle, stagger angle. Parallelly, we need to look at the parameters which are related with say aerofoil. Okay, let's see what all are the parameters. If you consider say I want to use a typical or special kind of aerofoil for my compressor development, then we have our fixed flow angle. That's what we have derived based on our pen paper calculation for the flow angles based on our expected pressure rise. Now here in this case we can have different combinations for this aerofoil to be possible. One of them, it says the thickness distribution of this aerofoil. So how my thickness it is been distributed on my camber line, that's what is one of the important parameter. we need to realize this aerofoil thickness, that's what is making our blade passage. And we should not forget, we are always talking in sense of diffusing passage. So the shape of this aerofoil, that's what is been decided by the thickness of my aerofoil. That's what is very important. Next, that's what is different kinds of aerofoil. We have discussed C4 aerofoil, we have discussed NACA aerofoil, we have discussed double circular arc, multiple circular arc, S type of aerofoil. So those all aerofoils, they are having a special application. We are expecting different kinds of loading on our aerofoil, or by using this aerofoil. We say we are looking for half loaded kind of configuration, we are looking for full loaded kind of configuration, we are looking for mid loaded kind of configuration. What all is this? We will be discussing in detail today. Next parameter, that's what is coming, is what is or varies by maximum camber. Okay, so this is what is representing location A, that's what is representing where I will be having maximum camber. At the same time, the location at where I will be having maximum thickness, that is also equally important. Okay, when I say aerofoil, we should not forget the shape of our leading edge and shape of our trailing edge. And as we have discussed, for C4 aerofoil, we are having leading edge radius to be larger compared to NACA 65. That's what is having advantages we have discussed in sense of incidence angles. Okay, same way for trailing edge also, for NACA 65 we are having sharp trailing edge, and for say C4 aerofoil we are having trailing edge with some radius. Okay, when we are discussing about the deviation angle, this all parameters, that's what is very important. Okay, so we can say this all are the parameters what we can play with in order to make our compressor. Okay, now the thing is, today we will be discussing how do we decide with the camber lines. Okay, so here if you look at, there are different types of camber lines which are people they have explored or which are available in open literature. And as on today, for running engines, this all kind of camber lines, they are been in use. Okay, some of them they are say circular camber line, parabolic camber line, polynomial camber line, exponential camber line, say DCA, double circular arc camber line, multiple circular arc camber line. So if you look at here, these two are mainly being used for subsonic aerofoils. Okay, and these others, they are being used for transonic aerofoil or supersonic aerofoils. Okay, so we will be discussing how do we derive or how do we get with these camber lines. And once we are having this camber line, how do we put our thickness on that camber line in order to make the aerofoil? Because that's what is of major concern to us. Okay, what design we have done, that's what is only pen and paper calculation. That is also important, but now once you have done that part, whole your work, that's what will be coming is with your aerofoil and your aerofoil selection and your aerofoil placement. Okay, so let's see, suppose we are taking first as a circular arc camber line. So here in this case, if you look at, this is what is representing C4 kind of aerofoil. We can say it is uncambered C4 aerofoil or symmetrical C4 aerofoil. Now, as we have discussed, these aerofoils, they are having special kind of thickness distribution. So the thickness distribution for C4 aerofoil, that's what has been given by this equation. Now, as I told, few aerofoils, they are available in open literature. So when you are starting with your initial design, or when you are started with your initial calculation or making a blade, you need to select those kind of aerofoils first. Okay, so suppose if you consider, say you are having the equation available for say C4 kind of aerofoil, so then we can say on this say straight line, this symmetrical aerofoil, this is what is giving the variation of my thickness. It says at 40% of my chord, I have maximum thickness. Okay, Now what we are looking for? We want to have this thickness distribution that need to be placed on my camber line. So I am looking for camber line. Okay, so suppose I say this is what is my camber line. In order to make that camber line, we need to have our angles. This angle we can say beta 1 and beta 2. They are nothing but my metal angles. When I say metal angles, do not forget we have discussed we are having our flow angle plus or minus incidence angle, and say our flow angle and my deviation angle. That's what will be giving us my entry angle, and outlet angle, that's what we have defined as our metal angle. So these are my metal angles. Okay. Now in order to make this camber line, we need to go with the mathematical formulation. So for circular camber line, this is what is my equation. What it says, my y coordinate for that camber line, that's what is a function of x and theta. This theta is nothing but that's what is my camber angle. Okay, so if we are putting different values of x and if we are putting the value of my theta, that's what will be giving me how my camber line, that's what is been prepared. So this is what is the formula for that. Okay, so now we are having our camber line, that's what is ready with. Okay, so those who are good in coding, maybe you can do practice, you can make a program, that's what will be helping you in playing with this camber line equation. Okay, now let's see. Now what we are looking for is we want to have this camber line that need to be covered with the thickness of my aerofoil. So here if you look at, this is what is my camber line, this is what is my circular arc camber line, and this is what is the thickness distribution of C4 aerofoil. Now in order to do that kind of calculation, we need to divide our surfaces in sense of upper surface, we can say that's nothing but my suction surface, and lower surface, that's what is my say pressure surface. Now when I say on my suction surface, I will be calculating my x and y coordinate based on x minus yt into sin phi. Here this is nothing but yc plus yt into cos phi. Same way I can calculate for lower coordinates. These are the equations for lower x and y coordinates. So more the number of blades you will be selecting, more will be the sharper curve you will be getting, or more accurate curve you will be getting. Okay, suppose say you are selecting less number of points, say you are selecting your x and y coordinates, that's what is less, it may be possible that you will be getting a zigzag kind of configuration for this making of this blade. So be careful, take these points in thousands so that it will give the smooth curve. Again, that's what is depending on what is your chord length. Okay, so here in this case, what phi we are looking for, that is nothing but that's what is the slope of my camber line. Okay, and what is my camber line? So here if you look at, this is what is my camber line. Okay, so this is what is my equation, and based on that we are calculating our phi at different location. Be careful. Say what we are doing, at different location we are getting our slope, and that's what we are putting in this equation, and that's how we are calculating our coordinates for upper surface, we are calculating our coordinates of lower surface. So this is how we will be making our C4 aerofoil at particular station using circular camber line. I am sure you are able to understand what we are discussing of. Okay, so this is what is one kind of configuration, that's what conventionally people they are using for the initial stage calculation. Okay, now let's move with say what all is happening. So here if you look at, this is what is representing, suppose if I consider this is what is my stage, say my rotor and stator. So for that configuration, for rotor if you look at, I will be having this kind of distribution. Okay, so you can see we are having our diffusing passage, that's what is making perfectly. Entry you are having lower area, at exit you are having higher area. Same way here if you look at, and this is what is representing at the tip region. So it says you are having smooth distribution of your thickness, and that's what will be giving you smooth passage, area passage, blade to blade passage we are discussing of. Okay. Now we have discussed when we are discussing about the change of stagger angle. So here if you look at, suppose this is what is at my hub, I can set that at stagger angle. We will be discussing all these aspects when we will be discussing the design in detail. There also we will be discussing how do we calculate or how do we determine the coordinates of these blades. Okay, so this is what is representing the staggered arrangement. Okay, so this is what we say in sense of our circular arc camber line. So most of the design, when we are talking about say our industrial fans, people they are preferred to go with this kind of configurations. Even when we are discussing about the HP compressor for gas turbine engines, for few stages on later stages, people they are preferred to go with this kind of camber line and C4 kind of configuration. Okay. Now let's say suppose I am looking for different other type of say camber line, where I will not be having our arc as circular one. Let's see, suppose here if you look at, this is what is having parabolic kind of configuration. So this is what is representing my chord length, say C, and here if you look at, this is what is representing my A by B. So for parabolic configuration you can say this is what is my location A and this is what is representing my location B. Again, as we have discussed, we are having angles as say my metal angle beta 1, my outlet metal angle, that's what is a beta 2. Okay. Now in order to have this parabolic camber line, this is what is the equation, that's what is available in the literature. Maybe you can use this equation for the calculation of say parabolic arc camber line. Okay. Now in order to solve this equation, we need to put certain boundary conditions. So what are the boundary conditions? Here if you look at, this is what it says 0 0 place, this is what is representing point AB and this is what is say C0. So I can say at Y0 we will be having 0, YC that is also 0, Y at A is my B number and Y dash A that's what is equal to 0. So if we are putting these angles into the configuration, we will be getting this equation. It says my 10 beta 1 that's what is given by 4B by 4A minus C, and 10 by beta 2 that's what is given by 4B divided by 3C minus 4A. So this is what will be giving us idea how do we do our calculation for say different parameters. That's what is say my A, B and C. Okay. Now what we know, if we consider we are more interested in sense of having our formula in the form of say camber angle. So we will be considering this equation, that's what need to be represented in the form of B by C, and that's what is a function of my camber angle. So the amount of maximum camber, so this location what we are discussing B and C, that's what can be calculated based on this formula. Okay, so this is what is the formula. If you recall my A by C ratio, again just remember A by C is nothing but that's what is representing my maximum camber angle configuration. Okay. Now this is what is the location of my maximum camber angle here. This is what we are discussing about. And if you will be solving this equation rigorously, you will be finally coming out with the equation of say the distribution of my camber line. It says that's what is given by x into bracket C minus x divided by this formula. Okay. Now you can understand we are moving towards the more complexity, and that's what is always required, the background of mathematics. So we will be taking this into configuration, and we will be moving with how do we use this equation for the development of our blades. So here in this case, again, in order to showcase what we have done, we have selected our C4 aerofoil. So this is what is representing my C4 aerofoil, and this is what is the thickness distribution for my C4 aerofoil. Based on our formula, we have derived with this curve, that's what is representing parabolic arc camber line. Now on this parabolic arc camber line, I need to superimpose this thickness. Okay, so again, that's what you can use the same fundamentals what we have used earlier. You will be calculating our upper coordinates, we will be calculating our lower coordinates, that means suction surface coordinates, my pressure surface coordinates, and that's what, based on my phi, I can impose them on my camber line, and that's what will be giving us, say, the blade, that's what is with required beta 1, beta 2 and thickness distribution. Okay. Now what is the beauty of this camber line? Let's see. So here if you look at, this is what is represented 4 loaded kind of configuration. So it says 4 loaded at 40% of chord. It has a specific meaning. So here in this case, if you consider, we know our fundamental. Suppose if I consider my flow, that's what is incident here. What is happening on our suction surface? We will be having more acceleration. That's what will be happening on my suction surface, and later on, after say 20% or 30% of chord, we will be having the deceleration. That's what is happening on the suction surface. Now what we are doing here, we have made this blade in such a way that that's what is 4 loaded. So you will be having whole lot of acceleration, that's what will be happening on the suction surface, and later on you will be having the deceleration of the flow. Now the benefit is in sense of CP distribution. You can understand, higher will be the acceleration on your suction surface, higher will be your area. So for special kind of application, for special kind of rotor at particular location, people, they are preferred to go with this kind of configuration. That's what we say as a 4 loaded kind of configuration. Here if you look at, this is what is representing my mid loaded kind of configuration. It says 50% chord, that's what is, we are having this camber line. Okay. Now I can change the shape of my, say, aerofoil by using this kind of configuration. It says aft loaded. So at 65% of my chord, I am having the turning here. Okay. So just understand like what all we were discussing about the circular arc camber line, where we are having our circular arc, that's what is not giving us any kind of flexibility in sense of changing the shape of my aerofoil. It is not giving any flexibility in sense of changing the shape of my blade at particular station. Here if you look at, this is also kind of aerofoil people they are using when they are looking for, say, aft kind of configuration. Okay. Here you can understand, if the flow is not well managed, there may be chances of flow separation to be happen near the trailing edge. Okay. Now this is what is representing, say, 40% chord, say 50% chord and 65% chord. You can understand here. Now if you recall, what we are basically looking for is, we want to manage our flow within 2 blades. So you can say this is my blade 1 and blade 2. If I will be going with what is happening with my flow, it will give me suggestion what all modifications need to be done. Let me tell you, here your computational study, that's what is coming into the picture. So you are starting with, say, some kind of initial guess with, say, circular arc camber line. Then you are having, say, flow physics, that's what you are capturing at different span of the blade. maybe 10%, 20%, 50%, 70%, 90% span. Then you are observing what is happening on my suction surface, what is happening on my pressure surface. If we are observing premature kind of flow separation, that's what will be giving us indication that there is something wrong at that particular station. Remember one thing, when we are saying we are having say separation of flow from the suction surface, that's what is acting like zero velocity. That means zero velocity, we can say it will be acting like a solid body. So rather at the exit we will be having our flow to be diffusing flow, it will be giving you accelerating flow. And that's where you need to play with the shape of your aerofoils. So this is what is very important for you to learn at this moment. Okay, here if you look at this passage area and this passage area, that's what is different. And here if you look at this passage area is totally different. Okay, so we need to do systematic study, we need to use the computational tool for this help, and accordingly we need to modify our shape of the aerofoil, we need to modify our camber line. Okay, now with these fundamentals, people they started exploring other possibilities. So other possibility, it says let me have flexibility. Let me decide from somewhere, I will be deciding with say having the curvature of my blade or curvature of my camber line. So here if you look at, this is what is representing double circular arc camber line. Okay, now if you look at this double circular arc, so I am having one circular arc and this is what is my circular arc 2. At some location I am defining as a junction. So this is what is my junction point. Now based on our understanding, based on our knowledge for say geometry, it says we need to have the continuous curve here, and that's what is being defined in sense of say junction angle. So here if you look at, this is what is representing my junction angle. So for double circular arc we are having more flexibility in sense of having junction point. That's what is giving us the location from where I want to change my shape of the camber line. It is also giving the flexibility of changing my angle. So are you looking for all of sudden change, or are you looking for say change with some reference? Suppose here if you look at for this kind of configuration, this is what is giving us sudden change of my say shape of the blade. Okay, now in order to have the flexibility, we are using this double circular arc camber line. So let's see, this is what is say two cases, we can say case 1 and case 2. For the same leading edge and trailing edge angle, we can say my delta beta, that's what I am looking for same, because that is what is my design requirement. Okay, we are having two different camber lines or two curves at this, that's what is present. I can say my junction point, that's what is placed at 40% of my chord. You can say this is what is my location. So on left hand side if you are looking at, we are having the turning of my flow, that's what is happening at 20 degree. Okay, and that's what is say having distribution in sense of 20 degree, and at the exit you are having 0 degree. Now if you are looking at on the other side, say this is what is say other kind of configuration in which we are having our flow turning, that's what is 30 degree, and that's what is giving me my exit angle as a 0 degree. So you can say we can decide the junction point, we can decide the junction angle, and that's what will be giving us the flexibility. Now here in this case, let's see, we can take, we are having the flexibility to move it say shifting of our junction point to say 65% chord as per our requirement. So this is what is my case. I can give my turning in such a way that I will be having the smooth curve on 65% chord location. Okay, so this is what is giving a more flexibility in sense of using the camber line. Okay, so for circular arc camber line, we are not having much flexibility. For say our parabolic kind of configuration, we have little configuration, that's what is giving us to move off load or say full load or mid load. But here in this case we are having too much of flexibility in sense of selection. Okay, so let's see, suppose if I consider this is what is representing mid loaded kind of configuration. For the same passage area, this is what is representing say full loaded kind of configuration, and here if you look at, this is what is representing my off loaded kind of configuration. So what sudden droop what we were looking for our parabolic arc camber line, that's what is now reduced. You're having more control of the flow on your suction surface, you have more control of your flow on pressure surface. Okay, now this is what is one of our own case study. So this is what we have used as a circular camber line. Okay, and that's what has been distributed with say C4 profile, and here if you look at, this is what is representing my CP distribution. Okay, and later on we have done our modification. Basically this is what is representing the stator. So at IIT Kharagpur we are having, say we are developing the test facility for highly loaded tandem bladed axial flow compressor. Now when we are having higher loading of say rotor, that means I'll be having higher turning of my flow, and that's what we are addressing by using say tandem configuration. Now since this is what is my stage, the turning that's what is coming out from my rotor, that need to give me axial outlet, and that's where my curve or say my delta beta or delta alpha for stator, that's what is coming very large, and that's what is making the design of the stator, that's what is very complex. And if you recall, we have discussed about the kind of stator what we have made. So there we have modified, we have used this double circular arc camber line, and here if you look at, this is what is representing the distribution of CP at 70% span. So we are having more control in sense of my pressure surface as well as on my suction surface. Now this is what is based on for our understanding. So here if you look at, this is what is representing my flow, that's what is incident on my stator at particular span, say for 10% span and 50% span. If you look at, this is what is giving me negative incidence angle, both the spans we are having negative incidence angle, and because of that you will see there is a premature flow separation, that's what is happening on the suction surface of my blade. If you are moving on say upper side, that means from 10% to 50%, where my flow separation is going large. And as I was discussing, if I consider this is what is my flow separation, this particular region, that's what will be acting like a solid body. And rather your flow need to diffuse, you can see my flow is getting accelerated, and that's what we are not looking for, because we want to diffuse our flow in stator also. Under that configuration we need to do modification with our profile, and that's what we have done by using double circular arc cambered stator. So here if you look at, this is what is a configuration, that's what is full loaded kind of configuration. So what incidence problem what we were having, that's what has been minimized. And if you look at, if you compare these two, you can say we are having our flow to be more touching with the suction surface, and we are able to minimize the flow separation, that's what is happening on the suction surface throughout the span. So this is how one need to understand, and this is how one need to apply the knowledge of what all we are learning with. Okay, and that's how you will be making your new configuration. So as I told, all compressors are unique compressors, all blades are unique blades. You cannot replace one compressor from one engine to other engine. All engines, they are having a special kind of rotor, they are having special kind of stators. Okay. Now this is what all we were discussing in sense of selection of circular camber line and parabolic camber line. What it says, my A by C ratio, that means my maximum camber, that's what need to be within the range of 0.3 to 0.6. So this is what is representing when we are having this in the range, that's what is giving us the high work absorption capacity as well as it is increasing our efficiency. So when we are making our camber line, we need to take care of selecting A by C ratio. Okay. Similarly, here if you look at, if we are looking for say smaller number, if we are having A by C ratio to be lower, then that's what you need to compromise in sense of your operating range. Okay, so it says smaller range, that's what will be giving you wider operating range. So you can understand what selection we are doing in sense of ratio of A by C, that's what is very important. Okay, now the situation where your maximum Mach number expected is small, this A by C ratio you can take as 0.5. So this is what is been given in open literature, and that's what many times we are following with, and as per our requirement, as I told, we need to change that. Okay, so you cannot go rigidly what say literature says or what book they are recommending. That's what is for special or typical kind of application. When you are doing your own design, that's what is a separate thing. It has nothing to do with what all that's what is available in open literature. Yes, the numbers what we are discussing, you need to stick with those numbers because that has come with a lot of experimentation, lot of experience. Okay. Now, if you recall, we were discussing about the calculation of my factor M. This factor M, that's what we are using for the calculation of our deviation angle. Okay, so this is what is representing my circular arc camber line. This is what is representing my parabolic arc camber line with different stagger angles. So we will be calculating our M factor based on that. Okay, now we have discussed what we say in sense of say maximum camber location. So here this is what is representing one of the aerofoil, that's what is with say circular arc camber line. And here if you look at, this is what is representing my what is happening on pressure surface, this is what is representing what is happening on my suction surface. So for this kind of particular circular camber line, if you look at, I will be having whole lot of acceleration, that's what is happening on my upper surface, and then my flow is getting decelerated. Similar to that on my say lower surface, on my pressure surface, I will be having little acceleration, and then we are having say deceleration of flow, that's what is happening. Now for same, if we will be using say parabolic camber line, just look at, this is what is representing half loaded configuration, and this is what is representing full loaded configuration. So here if you look at say my maximum camber position, that's what has been shifted towards the leading edge. Just compare these two, you will clearly see how my CP distribution that has changed. What we have done, we have just changed our camber line. Our thickness is same, our angles are same, but just look at, we will be having whole lot of acceleration, that's what is happening on our suction surface, and that will be followed by the deceleration, and on our lower surface or on my pressure surface, if you look at, we are having say acceleration of flow. Later on with this little deceleration, I will be having constant pressure kind of configuration. Okay, so this parabolic arc camber line with half loaded, you will be having this kind of CP distribution. Okay, similarly, suppose say if I am shifting my maximum camber on the later part, if you look at, just look this part, this is what is representing what is happening on my say upper surface or on my suction surface. I will be having little acceleration, but that will be followed by constant pressure, and then we will be having deceleration. That's what is happening on the later part of my blade. Okay, and same way on my say lower surface or on my pressure surface, I will be having flow acceleration that will be followed by say the deceleration of my flow. So, like this is what all we are looking for in sense of what we say half-loaded and full-loaded kind of configuration. Let me tell you, recent trend, that's what is going on, where people, they are defining this CP distribution. They say this is what is my CP distribution I am expecting from this aerofoil, and based on that, initially they will be assuming some aerofoil and they are doing inverse design. That means here, based on the shape of my aerofoil, we are getting CP distribution. By using numerical tool, what they are doing, they are having this CP distribution, that's what is available, and then after, based on that, they are doing or they are developing new kind of aerofoil. That's what is called inverse design kind of configuration. That is also a hot topic for the research. People, they are working on that topic since long, and now we are having again and again addition of new blade aerofoils. Now, if you recall, we have discussed different kind of configuration. We say we are having different kind of degree of reaction distribution. So here, if you look at, this is what is representing my degree of reaction to be 0, my degree of reaction to be 50%, and my degree of reaction to be 100%. You will say, sir, how we are correlating what all we learn with this degree of reaction? This degree of reaction, that's what we are looking for. What it say, my degree of reaction, that's what is 0, then I can say my diffusion is not happening in my rotor. Whole lot of diffusion, that's what is happening only in my stator. So if you look at the shape of my aerofoil, this is what is a constant area kind of configuration. Now you can say what angles we are deciding with. We are looking for the blade passage to be designed. We need to use the aerofoil. That's where what all learned, that's what is helping us. So you can see this is what is constant area passage. Here if you look at, my entry area is lower, my exit area is larger. Suppose if we are considering say 50% kind of configuration, again we are looking for different kind of aerofoils, different shape of aerofoils. Same way if you look at say for 100%, we are having say whole lot of work, that's what is only been done by rotor, and my stator, that's what is acting like a guiding the flow. So here we are looking for constant area passage for the stator. So the fundamental what all we learn about this aerofoil, that's what is straightway applicable for the design of our blade, and we know this degree of reaction, that's what is varying all the way from my hub to tip. Now you can understand what all angles we have calculated. It may be possible that throughout my span I will be having hundreds, thousands of aerofoils, and these all aerofoils that may be having different shapes. Okay, and how do we do the modification of those shapes? That's all what we have discussed today. I'm sure this is what will give you more clarity, more idea in sense of how do we move with the selection of aerofoil, how do we move with the selection of camber line after doing our design. Thank you very much for your attention.